Assalamu alaikum. What's up? This is Muhammad Ali, and today I will be talking about that how can we calculate the shear force and bending moment diagram for a particular loading case. And in order to understand the shear force and bending moment diagram, we are taking a very simple case in which we have the one load which is acting at the 2 meter distance from A point and also 2 meter distance from B point, or in other words, this is acting at the middle point from A and B. Now, in order for us to draw the shear force and bending moment diagram, the first step to do is to draw the free body diagram. And free body diagram is a diagram in which we represents the reaction forces as well as the external forces and nothing else. So we have this horizontal line is basically representing this beam. So since we have at a point of pin support, so we know this already that for the pin support we can represent the pin support with the equivalent of two loads, one vertical load which we will call as VA because this is a vertical load, it is acting at a point, so we are calling this as VA, and in horizontal loads which is we will naming that is HA. So these two load reaction loads will be there at the place of the this hinge support, while at the B point, because we have a roller support, so we will have a one vertical force and we will name this as VB. And as an external load we have the external load which is equal to 50 kilonewton, and this is acting at a distance of 2 meter from this side and 2 meter from this side. So this is our free body diagram, and after we have drawn the free body diagram, now we are ready to find out the support reactions. And in order to find out the support reactions, we have to apply the conditions of equilibrium. Now let's apply the conditions of equilibrium in order to find out the support reactions, and we know that there are three conditions of equilibrium. Number first condition is sum of all forces in x direction is equals to 0. Now because we have no any other force than in x direction other than HA, so we will say that HA is equals to 0. Now the second condition of equilibrium is sum of all forces in y direction is equals to 0, and we have three forces in y direction. We have VA, VB, and 50 kilonewton. But the point to note is that VA and VB are pointed towards the upward direction, while 50 kilonewton is pointed towards the downward direction. So VA plus VB, VA and VB will be positive because they are pointed towards the upward direction, while 50 kilonewton will be in negative direction because this is pointed towards the downward direction. So this is again with the sign convention that we follow, so this equals to 0. So this will give us the equation VA plus VB is equals to 50, and this is our equation number 1. Now let's apply the third condition of equilibrium. The third condition of equilibrium is sum of all moments about any point is equals to 0, and in this case we are taking a point as our the point at which we will be calculating the moments. So MA is equals to 0, sum of all moments about a point is equals to 0. Now because this is the a point and HA and VA both are crossing at a point, this is our a point, this is our B point, and this is our C point. And at the A point, because HA and VA are crossing over A point, so they will not have any moment because there is no any moment arm being generated by these forces. However, this 50 kilonewton force and VB force will have some sort of moment, and in order to calculate the moment generated by this 50 kilonewton and VB, we have to multiply the magnitude of these forces by the moment arm. And in this case the 50 kilonewton is at a distance of 2 meter from a point, so we will multiply the magnitude of the force, which is 50 kilonewton, by 2 meter, which is the moment arm, which is the distance between the point of application of the force to the point of rotation. And basically this will generate a clockwise moment. As you can see that this is making a clockwise moment at about a point, so this will be clockwise moment, while VB, the magnitude of VB will be obviously we do not know at this point, so we will write there VB, and then we will multiply this by the momentum, and the momentum for this case is 2 meter plus 2 meter, because the distance between the point of application of this force to the point of rotation is 4 meter. So this will be 4, but this will be anti-clockwise moment, and as you can see that this is generating an anti-clockwise moment about a point. Now this is equals to 0, Now 50 into 2 is equals to 100, and because this is a clockwise moment, so this is positive, and this will be minus 4 VB, minus because this is an anti-clockwise moment, and we know the sign convention. Now if we will move this 4 VB to the right direction, we will basically get VB is equals to 100 divided by 4. So this will give us the value of VB, which is equals to 25 kilonewton. Now if we will put this value of VB in equation number 1, if we will put this value in equation number 1, we will also get the value of VA. VA plus VB is equals to 50, and we know the value of VB, which is 25, so VA will be equal to 50 minus 25, so this will be equal to also 25 kilonewton. So the value of VA is 25 kilonewton and value of VB is also 25 kilonewton. Now this is a general conceptual as well. Now we can also see that because we have the 50 kilonewton force which is acting exactly in the middle, so we can also estimate from that that half of the load will be transferred to A point and half of the load will be transferred to B point. So from that we also could have judged that the reaction at A point will be 25 kilonewton and the reaction at B point will be also 25 kilonewton. Okay, so now once we know the shear force, we know the reaction forces. Now we will be able to find out the shear force and bending moment diagram for this whole beam. And in order to find out the shear force and bending moment diagram, what essentially we have to do, we have to basically find out the discontinuities in this whole beam. Or in other words, we have to find out that what are the sudden changes which are occurring in this particular beam. Now as you can see that from A to C, there are no any changes in terms of loading, and then there is changing at C, but from C to B there is no any changing in terms of loading. So what essentially we can say that we can divide this beam into two parts, AC and CB, and we will try to generate the equation which will be safely representing all the loading condition from A to C. So in order to generate the equation, what we essentially have to do, we have to basically, so we will try to divide this into two sections based on the loading conditions. So we are dividing this into two sections. One section is here, another section is here. We will name the section as AA and we will name the section as BB. Now after dividing this into two sections, we also need to specify the distances. Now in order for us to specify the distances, as we already know that the distances that we will take that part of the beam which is computationally less laborious. Now as you can see that if we are talking about the section AA, now all the forces which are left to that particular beam, we can also take all those forces and we can also find out the equation with all the forces which are right to this AA section. But as you can see that we have only one force basically because HA is equals to 0, but VA is equals to 25. So basically we have one force to the left of this AA section. So it is preferable and computationally less laborious that if we will take this VA force to the left of to the left of this particular beam, because this is computationally less laborious as compared to the right of that particular beam. And if we also talk about the section BB, now you can see that we can take the left of that particular section as well and the right as well. But as you can see that from left we have two forces, but from right we have only one force. So basically we will be taking a right portion of the beam for the section BB. So we have to specify the distances as well now, because we do not know the distance of AA, because we have assumed to be locating, we have assumed to cut this section at any place between A and C, so we will call this as distance X. And similarly for the section BB, we can call this as the distance X1. Now we can find out the uh, equations which will be representing the shear force and bending moment diagram for this case. Now for the section AA, whatever equation we will generate, that equation will be valid for the value of X which is greater than equal to 0 and less than equal to 2 meter. So this will be valid. All the equations which now we will generate will be valid only for the region of A and C. So now let's generate the equation for shear force diagram and bending moment diagram for this case. So for the shear force diagram, we know that we will take all the vertical unbalances from the left or either to the right, but because we have selected the left portion of the beam, so on the left portion of the beam we have only one force, which is VA, which is directed towards the upward direction. And we know this from the sign convention that all those forces which are directed towards the upward direction in the left portion of the beam, we call those forces to be generating the positive shear force. So this will be 25 positive, and because there is no any other force, so this will be, this equation will be only this 25. While for the bending moment diagram, the equation will be this force, uh, or will be basically the moment generated by all the forces to the left or to the right. But because we have selected the left portion of the beam, so we will find out the moment generated by this particular force at AA section. And in this case, the moment generated by this force at AA section is 25 into x, because x is the distance, s is the moment arm, and this will basically generate a clockwise moment. And again, we know this from the sign convention that the clockwise moments, if the we are taking the left portion of the beam, the clockwise moments are considered to be generating the positive bending moment. So we will call this as positive 25x. So we got the value, we got the equations for shear force and bending moment diagram for section AA. Similarly, for the section BB, we can also find out uh, the equations, but now we will be taking the right portion of the beam because this is computationally less laborious. So this will be equal to this section BB, whatever equation we will be generating, that will also be valid for the value of x1, which is greater than equal to 0 and which is less than and equal to 2 meters, or in other words, basically this represents the portion C and B. So for the shear force diagram, we have the equation for because we are considering the right portion of the beam. In the right portion of the beam, we have only one force VB, which is directed towards the upward direction. And in the sign convention, we know that the if we are taking the right portion of the beam, the upward forces are considered to be generating the negative shear force. So this will be basically minus 25. Okay, minus 25. Similarly, the equation for the bending moment diagram, the equation will be, equation for the bending moment diagram, we have to multiply all the forces by the moment torque. In other words, we have to calculate that how much moment is being generated by all the forces to the right of that particular beam or left of that particular beam by all the forces which are existing to the left or right. But in this case, because we have taken the right portion of the beam, so on the right portion of the beam we have only one force, which is equal to VB is equal to 25 kilonewton, and this will basically generate the moment of 25 into x1, because 25 is the magnitude of the force and x1 is the distance from the point of application of the force to the point of rotation. So this will be 25 into x1, and this will generate an anti-clockwise moment. As you can see, this is generating anti-clockwise moment. But from the sign convention, we know that if we are taking the right portion of the beam, then the anti-clockwise moments are considered to be generating the positive bending moment. So we will be considering this positive again. Now we have got the equations for whole the length of the beam. Now we can safely find out the shear force and bending moment diagram for whole length of the beam. Now in order to find out the shear force and bending moment diagram, I will basically uh, draw a line here, and this line basically represents the shear force diagram, which normally we draw below the loading case. So horizontal axis of the shear force diagram represents the length of the beam, while the vertical axis of the shear force diagram represents the magnitude of the shear force being generated at any point. Now for the section AA, or in other words for the portion A to C, we have the equation which is equal to 25. This basically means that from A to C we have a constant shear force of positive 25. Okay, But for the section BB, or in other words for the portion CB, we have the constant shear force of minus 25. So what essentially we can do that from C to B, we can draw the constant shear force of minus 25. So this basically is representing the shear force diagram, but we have to connect the discontinuities. So we are connecting these discontinuities. Now this diagram is representing the variation of shear force along the length of the beam. And as you can see that from A to C we have the positive shear force of 25 kilonewton, and then from the portion C to B we have the negative shear force of magnitude minus 25 kilonewton. So in the similar way we can also draw the bending moment diagram for this case. And bending moment diagram in this case, so in order to draw the bending moment diagram, I'm drawing a line which is representing the length of the beam, and this vertical axis is representing the magnitude of bending moment at any point. This will represent the magnitude of bending moment at any point. Now in order to draw the bending moment diagram, we have these two equations, this one equation and this one equation. This equation is valid from the point A to C, and this equation is valid from the point C to B. Now from, if we will uh, want to know the bending value of bending moment diagram at A point, what will be the value of bending moment at A point, then we have to put the value of x is equals to 0, because this x is the distance of this AA section from A point. And if we want to know that what is the value of bending moment at A point, we have to substitute the value of x is equals to 0. So if we will substitute the value of x is equals to 0, this whole equation will be 0. So what this essentially is telling us that at A point the bending moment will be equal to 0. Okay, so this will be 0 at A point, but at C point the value of x will be the value, because this is the distance from A point, the value of uh, x will be 2 meter, because C is at a distance of 2 meter from A point. If we will put the value of 2 in here, we will get the value of 25 into 2 is equals to 50. So this will give, this is basically telling us that at C point we have the positive value of bending moment, which is equal to 50 kilonewton meter. Now how we are going to connect these 2 points? This equation is again going to answer that question. Now because this is a linear equation which is representing the straight line, so we have to connect these 2 points by a straight line. Okay, and because this is a positive one, so this slope will be upward like this. All right, now for the portion CB we have this equation, and remember this x1 equation, x1 distance is from B point. So if we want to know that what is the value of bending moment at B point, we have to put the value of x1 is equals to 0. And if we will put the value of x1 is equals to 0, again this whole equation will be equal to 0. So this again is essentially telling us that at B point the bending moment will be 0. And now if we will put the value of x1 is equals to 2 in order to find out the bending moment at C point, so this will again give us the value of 25 into 2 is equals to 50 kilonewton meters. So this is basically telling us that from this point as well we will be getting the same value of bending moment. Now how we are going to connect this? Again this equation is going to answer that question, because this is a linear equation and this x1 distance is from the B point to C point and this is positive, so these are to be connected by a straight line. Okay, so this is our bending moment diagram. So this essentially is telling us that at A point we have the zero bending moment, and at B point we have also zero bending moment, but at C point we have the maximum bending moment, which is having the value of 50 kilonewton meter. Okay, now if you want to verify that whether you have found out these values correctly or not, you have to just go to the website, which is bending moment web diagram website. Go to this free calculator, beam calculator, and then you have to draw the same beam. This beam is having the length of 4 meter. At that beam we have the roller support at left end, and we have the we have the pin support at left end, we have the roller support at the right end, and we have only one load which is at a distance of 2 meter from a point, and its magnitude is 50 kilonewton. So this is the basically the bending moment. This is basically the scenario of the beam which we have just solved. If we will click the solve button, so this will automatically draw the shear force diagram and bending moment diagram. And you can see that the shear force diagram is same as that we have drawn from the equation, and bending moment diagram is same which we have drawn the equation, and maximum value is 50 kilonewton per meter. So I hope you guys have enjoyed this lecture. मिलते हैं अगले लेक्चर में. अपना बहुत ज़्यादा ख्याल रखिएगा. अल्लाह हाफिज़.